Welcome to this lesson on estimation and Fermi problems. This is another one of my favorite lessons in the entire course. I think it's one where you might be surprised by the skills that you're able to develop and the kinds of problems you can solve that would have before seemed unsolvable. So first, I should tell you what a Fermi problem is. And this is really just an estimation problem. It's a problem where you're trying to roughly guess, not guess, roughly make an educated guess about a quantity to get it to the correct order of magnitude. And you do this using minimal information, right? So the idea isn't you go look up a whole bunch of facts in Wikipedia or your library or something like that, but you're really just doing rough order of magnitude calculations. And if you don't know what order of magnitude means, I'm going to explain it to you on the next slide. The reason these are called Fermi problems is that they are sort of credited to this physicist named Enrico Fermi. He was a Nobel Prize-winning physicist. And the famous question he asked, that is a Fermi problem, was how many piano tuners are there in Chicago? That's something he tried to very roughly estimate. Now, there's two reasons I want you to have this skill of solving Fermi problems. One is that it provides a sanity check on other answers to other problems you might solve, right? So you're solving an applied mathematical problem, you have mathematics describing something in the real world, you do your math, you get an answer. You should always do a gut check and say, does this answer even make sense? And a Fermi problem is a way to do that sort of gut check estimation. Also, more to the point, sometimes estimating something is your only option, right? So there are some problems where to really solve them in a detailed way might take a lot of background information in mathematics that you might not even have access to, but you can always try to do a back of the envelope calculation, at least to get yourself started. So let's talk about what orders of magnitude mean. And in our base 10 counting system, order of magnitude just means the nearest power of 10 contained in a number. Or to make this very precise, you take a number, you take its log base 10, and you round that to the nearest integer, and 10 to that nearest integer is the order of magnitude, okay? So to do some examples, the number 126, which I've written here in scientific notation, has order of magnitude 10 squared because the log base 10 of 126 is 2.1. And if you don't remember how logs work, this means 10 to the 2.1 power is equal to approximately 126. So you take that log base 10, which is 2.1, you round it to the nearest integer so that it becomes 2, and the order of magnitude is 10 squared. Okay, here's another example. 2,946, which is written here in scientific notation, that has an order of magnitude 10 cubed because if you take the log base 10, you get 3.47. You round to the nearest integer, which is 3. Then you have order of magnitude 10 cubed. 3,425, which isn't so far away from 2,946. Here it's written in scientific notation. We say this is order of magnitude 10 to the 4th. Why? Because if you take the log base 10, you get 3.53, which to the nearest integer is 4, order of magnitude 10 to the 4th. What that means is that on a logarithmic scale, the number of 3,425 is closer to 10,000 than it is to 1,000. And finally, 0.0004, written here in scientific notation, this has order of magnitude 10 to the minus 3, because if we take the log base 10, we get minus 3.4 to the nearest integer, that's minus 3, and so order of magnitude 10 to the minus 3. Now, I'm going to run through a few skills, and these are skills that in a moment we'll try to put together to combine to be able to solve Fermi problems. One of the skills is to be able to multiply together sequences of numbers in your head and just do this sort of roughly and keep the result to one significant digit. So here's what I mean. Suppose an object is moving at 94 feet per minute for 23 minutes and ask you how far it moves, so you have to multiply those numbers. Well, you could use a calculator, or you could do it out with a pencil and paper, or maybe you could do it in your head if you're better at mental arithmetic than I am. But I would just estimate. So I would say 94 feet is close to 90 feet per minute, and 23 minutes is close to 20 minutes, and 90 and 20 are easy for me to multiply together. That's 1,800 feet. And so I would then round that to the nearest significant digit. That's 2 times 10 cubed, or 2,000 feet. And the true answer, if you multiply 94 and 23, is 2,162 feet. So my estimate was 2,000, real answer 2,162, not bad. Here's another example. An object has a density of 7.642 kilograms per cubic meter. The object has a volume of 3,718 cubic meters. What's the mass of the object? Well, you have to multiply the density times the volume. I cannot multiply those two numbers in my head, so I'm going to estimate, and 7.642, I'm going to round up to 8. 3,718, I'm going to round up to 4,000. 8 times 4,000 is 32,000. And then we can even go from there to one significant digit, which is 3 times 10 to the 4th kilograms. And the true answer you get from doing the multiplication is 28,413, pretty close to our 30,000 estimate. So that's great. The next skill is something called the geometric average. And you're going to learn some new terminology here, possibly. So the usual average that you might be familiar with is called the arithmetic average, or the arithmetic mean. And this has to do with addition, right? So the arithmetic average of two numbers a and b is just their sum divided by 2. Or another way of saying that is it's the number that's halfway between a and b in terms of addition. Fermi problems involve multiplication of a whole bunch of numbers. So it's going to be useful for us to know a geometric average, and this has to do with multiplication, and the geometric average is defined as the square root of AB, okay? And this is going to be something about what's in between two numbers sort of multiplication-wise. And so let me run through an example of this. The arithmetic average of 9 and 81 is 45, because 9 plus 81 divided by 2, 9 plus 81 is 90, 90 divided by 2 is 45. And another way of saying this is that 45 is halfway between 9 and 81 addition-wise, meaning there's some number, which happens to be 36, that if I add it to 9, I get to 45, and that's the halfway point, and then if I add that same number to 45, I get to the bigger number, which is 81. So 45 is halfway between addition-wise, okay? Now, what if we think multiplication-wise? The geometric average of 9 and 81 is 27, and the way you find that is the square root of 9 times 81, which is 27. And another way to think about this is that 27 is halfway between 9 and 81 multiplication-wise, because there's some number, which turns out to be 3, such that if I multiply 9 by 3, I get to 27, which is the geometric average, and then if I multiply by 3 again, I get to my larger number, which is 81. So arithmetic average here, geometric average here. This is the one, geometric average, is the one that's relevant to problems involving multiplication, okay? So building upon that, another skill that I want you to have is, in order to estimate a quantity, if you're really in the dark about something, think about successive orders of magnitude until you find one that feels right. If the choice between, oh, this should say TWO, 2 orders is hard, use the geometric average. And the geometric average of 10 to the n and 10 to the n plus 1 is 3 times 10 to the n to one significant digit. If that's too confusing, the geometric average of 10 and 100 is approximately 30. The geometric average of 100 and 1000 is approximately 300, and so on. That's a rule of thumb that you can use. So let's do some examples. Suppose I want to estimate the length of my small college campus, Macalester College. I don't know what it is, but I'm just going to start thinking about successive orders of magnitude. I can ask myself in my head, is the length of my campus bigger than 10 meters? Well, I know what a meter stick looks like. It's certainly way bigger than 10 meters. Then I can ask myself 100 meters, which is 0.1 kilometers. It even feels bigger. I can even imagine 100 meter sticks. It feels bigger than that to me. However, 1 kilometer feels too long. I know what a kilometer feels like from running, right? So 0.1 kilometers is too small, 1 kilometer is too long. I'm going to choose the geometric average of 0.1 and 1, which is 0.3 kilometers. That's my estimate. Here's another estimate. Estimate the weight of a pine tree, okay? I'm going to start with 100 pounds. Well, 100 pounds, that's less than I weigh. That's less than an adult's weight. A pine tree definitely weighs more than that. 1,000 pounds, that's probably the weight of about 5 or 6 adults. And that still feels too small to me. If I imagine the weight of 5 or 6 adults, and I imagine a big pine tree, the pine tree still seems bigger. So let's go another order of magnitude up from 1,000 pounds. Let's go to 10,000 pounds. 10,000 pounds, well, based on what we said before, 10,000 pounds would be the weight of 50 or 60 adults. That feels too big to me, okay? So I want to choose something that's between 1,000 and 10,000 pounds. So I'm going to choose the geometric average, which is about 3,000 pounds. Finally, this is perhaps the most important skill for Fermi problems, and it's the idea of breaking an estimation problem into subproblems. And the idea is to estimate each little part and multiply or divide all the answers together, rather than just guessing blindly. Right? So to make this concrete, here's our example. What is the population density of Los Angeles? I have no idea. Even if I try on orders of magnitude, 1 person per square mile, 10 people per square mile, 100 people per square mile, I have absolutely no idea. I'm just in the dark. So I'm going to try to break down the problem a little bit. And I'm going to remember that density is like a population per area, and that an area is like a length times a length. So I'm making lots of simplifications here. Like I'm going to imagine that Los Angeles is basically like a square, okay? And I'm going to try to guess at the length of a side of that square. That'll give me an area. I'm going to guess at the population, and if I divide those things, I should be able to get an average population density. Okay, so first let's try to estimate population. I'm going to try on successive orders of magnitude. 1 million seems way too small to me for Los Angeles. 10 million, which is the next order of magnitude, that feels a little big to me. I can think about the geometric average. The geometric average is 3 million. That actually seems too small to me. I grew up in Chicago. Chicago's smaller than Los Angeles. And I know Chicago has more than 3 million people. So I'm actually going to settle on this 10 million number, even though it feels a little big to me. We're estimating to order of magnitude. So we'll choose 10 million. That's 1 times 10 to the 7th people as the population. Next, we have to figure out the area. And like I said, to do that, I want to imagine a square that's the city, and I want to try to guess the length of one side of that square. 1 mile and 10 mile, those both feel too small to me. I mean, Los Angeles, you can drive for 10 miles, still be in that city. But if I go an order of magnitude bigger, 100 miles, that feels way too big to me to be the length of one side of Los Angeles. So I'll choose the geometric average of 10 and 100, that's 30 miles. Now that I've estimated a length, I can estimate the area. So again, based on my square, I'm going to have 30 miles here and 30 miles here. And if I square that, I get 900 square miles. But we'll go to, the closest order of magnitude, or one significant digit, and that's 1 times 10 cubed. I'm just going to round up to 1 times 10 cubed, or 1,000 square miles. Okay, that's our estimate. And so now I can put those things together. The density should be the population divided by the area. That's 10 to the 7th from up here, divided by 10 cubed from here, and that's 1 times 10 to the 4th. 10 to the 4th is 10,000. So our estimate is that the population density is 10,000 people per square mile. And then you can look up the value, and the true value is actually 8,225 people per square mile, at least in the place I looked it up. So you can see we got the right order of magnitude, and we weren't too far off just from our rough estimation. So let me try to summarize some of the skills and strategies we've talked about. When you solve a Fermi problem, break the problem down into subproblems. And you'll multiply and divide together the answers to those subproblems to get your final answer. For each subproblem, you make an educated guess. As hard as that is, you can try to feel out different orders of magnitude for each subproblem. If you can't decide between different orders of magnitude, choose the geometric average. These last 2 points are really important. Don't obsess over details. If you start making these problems too complicated, too detailed, you'll get stuck on them. Also, if you obsess about your accuracy, you're going to get stuck. So you have to accept what it means to estimate, right? So you have to accept that you might get a wrong answer, right? You're just trying to get a feel. If you're too concerned with getting a perfect answer, you will never solve the problem, and it's better to get an estimate than to get nothing at all. Okay, so those are my strategies, and let's go on and just do a couple examples. This one's about metabolism. We can ask, what is the metabolic rate in watts of a resting human? If you don't remember what a metabolic rate is or what watts are a measure of power. That was a little messy. Watts are a measure of power, right? And power is energy per time, okay? So that's what we're estimating, energy per time, metabolic rate of a human who's resting. So energy per time, we're typically going to measure in joules per second. That's what watts are. Watts are joules per second. And I have no idea what this is for a human, but we can sort of guess that if a human isn't gaining weight or losing weight, that means that they have to burn as much energy per day as they take in. And the way you take in energy is by eating. And I sort of know as a rule of thumb that an adult eats somewhere around 2,000 calories per day. So when we say calories, this actually means kcal, which is technically kilocalories. But when you hear people say food calories, that's what they mean. So 2,000 kilocalories per day. So let's assume that a person's eating 2,000 kilocalories per day and burning that much, and that they're staying at a constant weight. Again, these are simplifying assumptions, but that's okay. We want to have an answer that relates to joules, so I'm going to actually look up a conversion factor that that 1 kilocalorie is 4,184 joules. And then I'm going to use our unit conversion skills here. I have 2,000 kilocalories times 4,184 joules per kilocalorie equals 2 times, and I'm going to estimate this in my head now, right? So rather than doing this exactly, we'll do 2 times 10 cubed kilocalories. There's no rounding to do there. Here we'll just round this to 4 times 10 cubed joules per kilocalorie. So the kilocalories will cancel out. I can do 4 here times 2 here is 8 here, and 10 to the third times 10 to the third is 10 to the sixth here. So my estimate in my head is 8 times 10 to the sixth joules. So to sum up so far, 2,000 kilocalories is 8 times 10 to the sixth joules. Okay, next step is to get seconds from days, right? So we have 1 day times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And you can see that the days will cancel out, the hours cancel out, the minutes cancel out. You're going to be left with seconds, and the number is 60 times 60, which is 3,600 times 24. 3,600 times 24, I can't do that in my head, but 3,600 is close to 4,000, 24 is close to 20, 4,000 times 20 is 8 times 10 to the fourth, 80,000 seconds, okay? So to summarize that bit, the number of seconds in a day is approximately 80,000. Okay, now energy per time is just our energy of 8 times 10 to the sixth joules divided by our time of 8 times 10 to the fourth seconds, right? So the 8s divide out, 10 to the sixth divided by 10 to the fourth is 10 squared, which is 100, and joules per second is watts. So our answer is about 100 watts. Okay, this is approximately the wattage of a light bulb. This example is about babies being born, how many babies born in the world each day, and we'll make some simplifying assumptions. Let's start by trying to outline the basic strategy. We're going to assume the world population is steady, which means that however many people die each day, that's how many people are born each day. We know that the world population is growing, but that just makes this problem even harder. Let's assume that world population is not growing. Our strategy is going to be to estimate the number of deaths per day from knowing the lifespan of people, which we'll also guess, and you'll see how that works. And then we need to figure out the population of the world. So population of the world, 1 billion seems small to me. I know it's more than 1 billion. 10 billion seems big to me. Geometric mean of those is 3 billion. That still seems small. I know that some years back it was 5 or 6 billion. So we'll go with our bigger estimate. We'll go with a world population of 10 billion. Again, it's an order of magnitude estimate. Now for the lifespan, let's see, what's the lifespan? How long does a human live? 10 years, that feels too small to me. 100 years, that feels too long to me. Most humans don't live 100 years. We could take the geometric mean. Geometric mean is 30 years. Wait, that feels too small to me, actually. So we'll go with our bigger estimate. We'll go with 100 years. It's an order of magnitude estimate. It's probably a little big, but that's okay. Now, we're going to assume that the population is distributed equally across all ages, right? Like, there are as many 1-year-olds as there are 2-year-olds, as there are 3-year-olds, as there are 99-year-olds, as there are 100-year-olds. And when everyone reaches age 100, they die, right? So this is, again, a very big simplification, but we're just going to say that If the lifespan of people is 100 years and the world population is staying constant, that means about 1/100th of the population dies every year. Okay? So 1/100th of that world population of 10 billion is 100 million, or in scientific notation, that's 10 to the 8th deaths per year. Since there are 10 to the 8th deaths per year, we can convert that to deaths per day. So unit conversion factor of 1 year per 365 days. I can't do this in my head, but 365 is approximately 3 times 10 squared, right? About 300. 10 to the 8th over 10 squared is 10 to the 6th, and then 1 over 3 is a third. So 1/3 of 10 to the 6th deaths per day is approximately 3 times 10 to the 5th deaths per day. It's a rough approximation. And then, since there are 3 times 10 to the 5th deaths per day, we'll say that if the world population is steady, there's the same number of births. So that's 3 times 10 to the 5th, which is 300,000 births per day. That's our estimate. Now, if you try to look up the true value of this, you'll see slightly different values in a range, maybe a range between 200 and 400,000. I saw the number about 360,000 pop up quite a bit. That's not far from our estimate of 300,000. Okay, so this is the end of the lesson. I want you to reflect on the following things. I want to ask yourself if you can identify the order of magnitude of a number, if you can multiply and divide numbers to one significant digit in your head, if you can compute the geometric mean of two numbers, if you can estimate simple quantities by systematically guessing orders of magnitude and using the geometric mean if you can't decide, and finally, if you can put it all together by constructing answers to Fermi problems by breaking down an estimate into its constituent parts. I really encourage you to exercise this skill. It's useful and it's fun. Okay, thanks for listening.